Hey everybody, in this quick video I'm going to talk about how we can use map patterns to discriminate different geologic features, especially in satellite images or aerial photos that are collected from above over a large scale. So what do I mean by map pattern? I mean when you're looking down from space or from the air, what is the pattern that the rocks are defining? What patterns can you see with your eyes? And what can you infer from that about the geologic context? So for example, what we see here is kind of an S pattern like this. Okay? And then within this kind of fold right here, we see another bed right here. So right away, these kind of sequences of linear ridges that are folded and creating these kind of envelopes, I know right away these are folded sedimentary rocks in the Valley and Ridge province of Pennsylvania, just from that map pattern. And these are sedimentary beds. So I want to talk a little bit about how we can make these types of inferences from map pattern. So I'll start with sedimentary rocks. So essentially, when we're interpreting sedimentary rocks, we need to understand that sedimentary rocks are made of planar beds that can differ in strength or erosion resistance and color. And these planar beds are essentially intersecting the surface. So in this picture, we've got these planar sedimentary beds, alternating colors. And you see they're coming up and they're intersecting the somewhat flat surface here, okay? So when you look down from above on these, what you're going to expect to see, if the surface is flat, you're going to expect to see these planar beds essentially as lines across the surface, okay? However, if the surface is not flat, like right here, the surface steps up, then what you see is going to depend on how the sedimentary bed is oriented relative to the surface. And in this particular case, this surface is actually the bedding surface. So literally this surface on the landscape is actually also the surface of a planar sedimentary bed. And that's quite common for sedimentary rocks. So this is fairly complicated. This sketch or these set of diagrams helps you think about that. And what you're really thinking about is how a planar object intersects a complex surface. So for example, if you have a relatively horizontal sedimentary bed, they're going to trace a contour through the surface here, perhaps. If you have a relatively vertical sedimentary bed, let's say down here, it's going to trace more of a line across the surface. So you can study this diagram. It's pretty interesting. Another example of sedimentary rocks that we started with is folded rocks. So here's a classic example, the Sheep Mountain Anticline in Wyoming. And you can see that these beds form this kind of concentric ring. So the fold was an arch. So it was a convex arch or an anticline like this, okay? And you can see that this is the same sedimentary bed that's tracing all the way around here. And this three-dimensional fold, once the three-dimensional fold was eroded and the top was removed, all of the overlying rock was removed over time, it kind of wore down into the center of this fold, and you can actually see these rings or concentric beds delineating the fold. Also note, this is very common with sedimentary rocks. Some of them are more erosion resistant, so some of them are actually sticking up and out, while others that were softer and more easily eroded are recessed or even covered. It's quite often in sedimentary terrains that weak erodible rock units are covered by sediment, whereas the erosion resistant ones are emergent. Okay, so let's think about igneous rocks now. So igneous rocks, you probably know, are formed from magma that comes up from the subsurface. And kind of by definition, that magma has to be intruding upwards into something, right? So here's what we think of a batholith or a big magma chamber. This magma burned its way or melted its way up to the surface. And so because igneous intrusions often had to come later, we'll often see that their contacts can be sharp. There's often a sharp contact, of course, particularly when the igneous feature post-dates the country rock. Depending on the nature of the igneous feature, if it's a dike, we'd expect to see perhaps a linear expression, right? Dikes are planar sheets of magma and often will be showing up as fins or other linear features here. In other cases, if it's like a sill or a batholith, we may expect to see a circular feature like this. Another thing about igneous rocks is they are often erosion resistant. So we often think of igneous rocks like granites or basalts as tending to be more prominent in the landscape because they're a little more resistant to weathering. Here's a couple examples. Here's the Sierra Nevada, California. We've got a granitic pluton in contact with some of the overlying country rock that was there previously. And notice how sharp that contact is. These two broad colors that are kind of consistent. And then over here we have a more zoomed out map view, so looking straight down from a satellite of the Brandberg Massif in Namibia. This is a deeply eroded pluton, and you can see this is perfect. It has a circular shape, and then you can see the really sharp contact with the country rock around it. So that's and of course it has the positive relief. It is the granite here, or igneous rock, is standing a little bit higher than the surrounding country rock. Okay, metamorphic rocks are really quite complex and are kind of difficult to summarize in this short video. They tend to have ductile folds or elongated fabrics or stretched fabrics. So they can look almost anything. They can look somewhat like sedimentary rocks if you're catching some of these fabrics. They can be folded. They can create small-scale or large-scale folds across the landscape. They're often weathering resistant, not always, but because the metamorphic process tends to sinter and consolidate rocks into things like quartzite and gneiss, those metamorphic rocks often do have a positive relief in the landscape. Okay, so let's finish briefly with faults. Three types of faults. One type is a strike-slip fault. You see this fault here. This is the San Andreas Fault in California. This is the Los Angeles Basin over here. And strike-slip faults are vertical, typically, which means that they intersect the surface of the Earth in a very linear way, right? So here's the vertical San Andreas intersecting the California crust. They often have a topographic depression at a small scale, like this mountain valley, and they can also juxtapose topography. So they can slide larger mountain ranges, like this block, up against valleys, where you can see clearly that sudden change from mountain range to flat valley actually results from one block being slid laterally past the other. Normal faults also tend to be very high angle, which means they intersect the surface at a relatively steep, relatively linear trace. This is a normal fault in the Tetons near Jackson, Wyoming. And you can see it's cutting here, cutting across a glacial moraine in a pretty linear expression. This side has dropped down relative to this side. It's quite often with normal faults that because they're dropping one side down, you'll see them associated with steep mountain range fronts and also often with triangular facets. You can see as this fault continues to drop down, it's leaving this kind of triangular faceted ridge or a truncated ridge that can be quite diagnostic. And then finally, the third type is thrust fault. Thrust faults tend to be low angle, as shown here, maybe anywhere from 10 to 30, 40 degrees, which means they intersect the surface at a shallow angle, and they tend to express themselves more as a topographic contour, where the trace of the thrust actually contours around a certain elevation, kind of stays at a specific elevation, which can often put them at the base of topography, near range fronts, or if there's actually an anticline growing above the thrust. That's another reason you'll often see thrusts popping out just at the outboard side of a ridge, if that ridge is a growing anticline. And I'll just close here with some geomorphic features, and these are alluvial or fluvial deposits, okay? So here we have an alluvial fan emerging from a range front. Actually, this might be a faulted range front, normal fault. Here we have a Landsat image of a fluvial river valley. Okay, so here's a dammed lake with a river valley coming down through it. So how do we spot these things from above? Of course, river valleys and fans are often less vegetated. They're often channelized. Of course, river valleys themselves are often flat and relatively low relief as well, whereas alluvial fans often have a conical shape. And of course, river valleys have a river running down the middle of them. Okay, well that does it. I hope you have a sense of what you're looking at in these satellite images now. Thanks for listening.